In the name of Almighty God, I'm Master Sankosha, and today I want to talk about mental processing module in COMSOL multiphysics simulation software, defining multiphysics models. This chapter describes how to couple the phase transformation interfaces to the heat transfer in solids and solid mechanics interfaces. A good place to start reading is in building a COMSOL multiphysics model in the COMSOL multiphysics reference manual. In this chapter, a heat transfer with phase transformations for modeling phase transformations, coupled to heat transfer. A steel quenching for modeling the specific case of austenity, the composition coupled to heat transfer and solid mechanics. Induction hardening for modeling induction hardening processes, including phase transformations in a steel coupled to heat transfer, solid mechanics, and magnetic fields. The next one is phase transformation, latent heat, a predefined unidirectional coupling that adds a latent heat from phase transformations as a heat source term in the coupled heat transfer interface. The next one is heat transformation strain, a predefined bidirectional coupling that is used to transfer strain and stresses to and from the coupled solid mechanics interfaces. Now I want to go through the heat transfer with phase transformations. Heat transfer with the phase transformations, the multiphysics interface combines the metal phase transformation interface with the heat transfer in solids interface. Phase transformations are generally temperature dependent, and this interface is suitable starting point for modeling metallurgical phase transformations that occur during a thermal transient. Latent heat is generated during phase transformations and the interface transfers this generated heat to the heat equation that is used by the heat transfer in solid interface as shown in figure 2-3. This is done using the phase transformation latent heat multiphysics coupling. Figure 2-3 illustrates the constituent interfaces of the heat transfer with phase transformations, a multiphysics interface. You see that we have a metal phase transformation in the left section by the directional of latent heat reached to the heat transfer in solids and bidirectional by the heat and temperature. Steel quenching. The steel quenching multiphysics interface combines the austenite decomposition interface with the heat transfer in solids and the solid mechanics interfaces. It can be used to study heat treatment processes by which steel parts which have been heated to a fully austenite stage are quenched. The multiphysics interface couples the constituent interfaces so that effects of the latent heat and phase transformation strains can be included in the analysis. Phase compositions, distortions, and residual stresses can be computed using the sequencing multiphysics interface. Figure 2-4 shows how this information is passed to and from the austenite decomposition interface. Note that, for example, material properties used in solid mechanics can be temperature dependent and that plastic dissipation can act as a heat source in heat transfer in solid. This is not shown in the figure 2-4, the sequencing multiphysics interface uses the phase transformation latent heat multiphysics coupling and the phase transformation strain multiphysics coupling. Figure 2-4 illustrates the constituent interfaces of the steel quenching multiphysics interface. For an example how to use the steel quenching interface, see carburization and quenching of a steel gear. Application library path is metal processing module slash steel quenching slash carburization and quenching of a steel gear. Induction heating section. The induction heating multiphysics interface combines the austenite decomposition heat transfer in solids and solid mechanics interfaces with the magnetic fields interface. This is the most specialized interface of the metal processing module. Its purpose is to simulate the particular heat treatment processes where a steel part is induction heated using a coil and subsequently quenched. The multiphysics interface coops the constituent interfaces so that effects of latent heat, phase transformation strains, and the electromagnetic heating can be included in the analysis. Figure 2-5 shows how this information is passed between the interfaces. Phase composition, distortion, and residual stresses can be computed using the induction hardening multiphysics interface. You see figure 2-5 illustrates the constituent interfaces of the induction hardening multiphysics interface. For cooling, the multiphysics interface is identical to a steel quenching multiphysics interface, but in order to model induction heating, a magnetic field interface is used together with an electromagnetic heating multiphysics coupling. Note that the austenite decomposition interface used in the induction hardening multiphysics interface doesn't add phase transformation nodes for heating. Depending on the phase composition of the steel prior to the induction heating and depending on the level of modeling detail that is warranted, one or more phase transformation nodes should be added to model austenitization. Austenitization. Now I want to go to the phase transformation latent heat. This unidirectional multiphysics coupling generates a heat source term in the heat equation of the cooled heat transferring solids interface. The heat source terms correspond to the latent heat produced during phase transformation. See phase transformation latent heat in the theory chapter. Phase transformation strain. This bidirectional multiphysics coupling is used to transfer strains and stresses to and from the cooled solid mechanics interface. If enable transformation induced plasticity is selected, the stress tensor from the solid mechanics interface is used to compute TRIP strains during phase transformations. These strains are used by the solid mechanics interface as an inelastic strain contribution. If enabled thermal strains is selected, the thermal strains are used by the solid mechanics interface as an inelastic contribution. When you use this coupling, you should not use the thermal expansion node to compute thermal strains to be used in the solid mechanics interface. If enable phase plasticity is selected and if the plasticity subnode under linear elastic material is used by the cooped solid mechanics interface, the equivalent plastic strains is transferred to the phase transformation interface. This way, the individual hardening function for each phase can be evaluated. Annealing chapter. An annealing subnode can be added to the phase transformation strain multiphysics coupling. This subnode is used to specify an annealing temperature above which plastic hardening variables, equivalent plastic strains, are set to 0. The annealing multiphysics subnode must be used in the conjunction with the annealing subnode to the plasticity in the cooped solid mechanics interface operating on the same selection. TRIP strains, thermal strains, and the plastic strain tensor are all affected by the annealing subnode. Now I want to go through the selecting discretization, phase transformation modeling. The metal phase transformation acetate decomposition and the alpha beta phase transformation interfaces provide a discretization for phase fractions setting. This is used to set the shape function order for the phase fractions and it should match the settings for the temperature field used by the heat transfer in solids interface. It is set to quadratic by default to match the default settings of the heat transfer in solid interface. Now I want to go to the carburization model. The discretization setting of carborization interface control the shape function order for the carbon concentration. The element order is set to quadratic by default. It is specified for shape shifter. Using effective material properties. When a material undergoes phase transformations during a thermal transient, its material properties will change. The properties are typically temperature dependent and tend to be phase dependent too. For example, the initial yield stresses at a given temperature will be higher in a martensit than in ferrite. Two metallurgical phases that appear during hardening of steel when the metal phase transformation austentate decomposition or alpha beta phase transformation interface is used with heat transfer in solids or solid mechanics. It can compute effective material properties that can be utilized by these interfaces. The benefit is that the heat transfer in solids and solid mechanics interfaces themselves don't need to perform phase averaging of the material properties that are used. You can generate a compound material that can be used by other physics interfaces as a domain material. The compound material is created if you use the Create Compound Material option at the physics interface level. This material contains effective material properties that are computed from the corresponding material properties defined for each phase. Note that if Enable Phase Plasticity has been selected at the physics interface level, the user-defined option should be used for the isotropic hardening model in the plasticity node in solid mechanics. Thank you so much for watching my tutorial video until the end. Today is 27th of May 2026. Time is 7:26 p.m. And also you can download the proper, appropriate, and related COMSOL multiphysics simulation file from my github.com/masterscript.